everyone, welcome to our podcast, Heat, Energy, and Everything in Between. Here we will dive into the world of transport phenomena, where we will discuss and study how momentum, energy, and mass move through material.
I'm Shivangi. In chemical engineering, transport phenomena is very crucial. It tells us how substances heat up, cool down, and diffuse in various processes.
Exactly. Today we are focusing on heat transport, specifically on shell energy balance. This helps us analyze how thermal energy flows through material. We'll also explore the related concepts like Fourier's law, boundary conditions, and some real-world engineering applications.
So, whether you're a chemical engineering student or someone who's curious about heat flow, stay with us for the next hour and uncover the mechanics of thermal transport in electric heat sources.
The shell energy balance is a fundamental concept in transport phenomena used to analyze the energy movement in a differential volume within a system. Now, let's break it down step by step.
Great. What exactly shell energy balance is?
होता क्या है? Shell energy balance is a mathematical representation of energy conservation within an infinitesimally, मतलब बहुत छोटा ही controlled shell or volume in a material. It considers energy coming in and energy going out, energy generation within the shell, and energy accumulation.
Okay, now let's first define the system. We define a thin control volume or a thin shell within the material. This shell has thickness dx along the x direction and a cross-sectional area of A.
Right. The idea is to apply an energy balance to this tiny region and derive a differential equation for temperature distribution in our case. Okay, so now we have defined the system. But Shivangi, do you know we are doing shell energy balance? So the general energy balance equation, do you know anything about that?
Yes, the general जो energy balance is energy in minus energy out plus energy generated equal to the total energy accumulated in the system.
Yes, but here
This is
in
a general.
Yes, but here in steady state, the following the question what we are going to do, we have a steady state. So in steady state, accumulation will be zero. So now the
Right.
general equation will come down to energy in minus energy out. The generated is equal to zero.
Right. Okay, so far we have seen the generalized equation. Now let's dive into the detailed version of it. It is rate of energy in by molecular transport minus rate of energy in out by molecular transport plus rate of energy in by convective transport minus rate of energy out by convective transport plus rate of work done on system by molecular transport minus rate of work done by the system on molecular transport plus rate of work done on system by external forces plus rate of energy production. This all equals to 0.
Okay, so now let's dive into the detailed explanation of each of the terms. So what basically is convective transport? So why does energy transfer occur by convective transport? So basically होता क्या है? तो convective transport mainly bulk motion के वजह से होता है. So convective transport of energy occurs because fluids have the ability to move, carrying energy with them. Unlike conduction, which relies on molecular motion, molecular interactions, convection happens due to bulk motion. So this transport is mode is dominant in systems where there is fluid flow and a temperature difference. Basically, the key reasons for convective energy transport, there are some key reasons. So, bulk fluid motion is one of them. So, when a fluid flows, it carries internal energy that is also called a sensible heat with it. So, if the fluid flows, if the fluid is hot, it brings thermal energy into a new region. If it is cold, it removes energy from the region. Then temperature gradients due to that also, so convective energy transport occurs when there is a temperature difference between a moving fluid and its surroundings. Heat naturally flows from a high temperature region to a low temperature region, obviously. Now, there are two types of convection. One is forced, one is natural. So, forced convection occurs when an external force drives the fluid movement. And natural convection occurs due to density differences caused by temperature variations and etc. Now we'll see why does energy transport occur by energy transfer by molecular transport occurs. So energy transfer by molecular transport occurs due to random motion of molecules, unlike in convection. So unlike convection, which involves bulk fluid motion, molecular transport happens even in stationary fluids and solids. So it is responsible for heat transfer to conduction and diffusion. Now, there are some reasons for molecular transport also. So some are like molecular motion and collisions. So at microscopic level, molecules are always moving due to internal energy. So when fast moving, that is high energy, high kinetic energy molecules collide with slow moving energy molecules, they transfer energy that basically leads to heat conduction. Now, temperature gradient also cause conduction. Heat flows from a higher temperature to lower temperature due to difference in molecular energy. Now, this is governed by Fourier's law of heat conduction. The third one is energy transfer via molecular diffusion. So, in multi-component systems, molecular transport can happen through diffusion, where different species move due to concentration gradients. This affects the transport of chemical energy in reacting systems. Now, now most obviously, so your difference from convection, we discussed earlier that convection is due to bulk motion. So in naturally here, no bulk motion is required. So unlike convection, molecular transport happens even in solids and does not require fluid motion. This is why metals conduct heat efficiently, even though they do not flow like fluids. We have discussed the first two main parts, convective and conduction. Now we moving forward. The next term is rate of work done on system by molecular transport minus rate of work done by system by molecular transport. Now we'll think that this is similar to the above part which we discussed just previously, but this part is more like convection. It is not basically related to molecular transport. So in this context, the transport phenomena, molecular transport doesn't just move or move mass or energy. It can also transfer mechanical energy such as momentum and work. This is particularly important when considering viscous forces and fluids. The term accounts for mechanical energy exchange due to molecular level interactions, especially shear stress from viscosity and normal stress from pressure difference. These forces can do work on the fluid element or have work done by the fluid element. Now let's define it properly. So in a differential shell element, the rate of work done by molecular transport includes two things. First is viscous force, that is shear work. This is the mechanical energy transferred due to viscous stresses as layers of fluid slide past one another. And the next one is not much common, but in some cases, when fluid molecules move in or out of control volume under pressure, they may do pressure volume work. And this is known as pressure work. Okay. So now the next term is rate of work done on system by external forces. So now, rate of work done by external forces is a crucial part of the shell energy balance transfer phenomena, which often includes pressure forces, gravity, electric fields, or electric energy something, and other external influences acting on fluid elements. So what does this term exactly mean? So when external forces act on a system or control volume, they can do work, that is transfer mechanical energy into the system. This increases the energy of the fluid and must be accounted for in the energy balance. So now different types that we discuss: pressure, gravity, and electric. So types of external forces that can do work: pressure forces, commonly in fluids. So pressure acts normal to the surface that can push the fluid. As fluid moves under pressure, it does pressure volume work. Now, the next one is gravitational forces, and one is electric. Like in this question, we'll discuss more about electric energy. Now, the last term that we have to discuss here is rate of energy production. Now, this term in shell balance is often referred to as a source term and plays a critical role in accounting for internal energy changes due to chemical, nuclear, electrical process. Like in this case, we'll be discussing about electrical process. So this term represents the rate at which energy is generated or consumed inside the control volume due to internal sources, not due to transport, due to internal sources. Now, source of energy production, as we discussed, chemical reactions or nuclear reactions or electrical sources. Like in this question, we are studying flow through electrical current flow through wire, and one is viscous dissipation. Like in highly viscous flow or flow past shear layers, we discussed earlier, mechanical energy is converted into internal energy heat.
Now we have seen शेल एनर्जी बैलेंस मतलब उसमें होता क्या क्या है हमने सारे पार्ट्स देख लिए कि अब उसमें की कंपोनेंट्स क्या क्या कन्वेक्टिव कन्वेक्टिव के कारण कंडक्शन के कारण वर्क डन एक्सटर्नल फोर्सेस मतलब सारी देख ली अब नाउ व्हेन सॉल्विंग हीट कंडक्शन प्रॉब्लम्स इसमें एक और बहुत इंपॉर्टेंट चीज होता है जो कि हम लोग सॉल्व करने में यूज होता है जो कि होता है बाउंड्री कंडीशंस नाउ बाउंड्री कंडीशंस आर क्रूशियल because they help define the behavior of heat transfer at system boundaries, ensuring that differential equations yield meaningful and physically accurate solutions. They define how heat is transferred at the surfaces of the system and help determine the temperature distribution.
Exactly. Boundary conditions are variations solving the question. There are mainly four key boundary conditions. We'll be seeing each and every in detail now. First is specifying the temperature. As the name suggests, what is in it is we specify the temperature of the system at the boundary. For example, if one end of a metal rod is maintained at 100 degrees centigrade, and then at that boundary, the temperature will always remain 100 degrees centigrade, regardless of the heat transferring in the system or not. This is our first condition. Mathematically, this condition is expressed as T of x equals to T naught. That is, at a particular distance x, the temperature will always remain constant, that is T naught, which we have defined. Okay. This boundary condition is often used in cases where we have a surface direct contact with a heat reservoir or a controlled temperature environment. Now, this is our first condition. Now we'll be going to the second condition, which is somewhere similar to our first condition only. Second condition is specifying heat flux. Here, just like in the first condition, we have mentioned and specified the temperature at the boundary. In this, we specify the heat flux. So, just like the first condition, we will see in the second condition. In first condition, we have specified the temperature. Let's say now we do not have the temperature. In this, we can specify the flux. So, our second condition is specifying the flux at the boundary. What does it mean? This means we define the rate at which heat is added or removed. Real world example would be insulated walls where no heat is allowed to escape. Since no heat flows out, the heat flux at the boundary will be zero. We can express this condition in mathematical terms like minus k dt by dx equal to qs. Qs is a specified heat flux at the boundary. Now, let's say if a boundary is insulated. In that case, what will happen? In that case, our Qs will be zero, as no heat is being transferred. That means dt by dx will become zero. What does that mean? That means temperature gradient will become zero.
So we have seen the first two boundary conditions. Now the next one is basically continuity of temperature and heat flux. और इसमें होता क्या है कि for example assume कि दो materials simultaneously एक दूसरे से connected है जैसे कि आयरन एंड एल्यूमिनियम तो दोनों के बीच में हम लोग ने बाउंड्री कंडीशंस क्या लगाने हैं कि मतलब इजी हो जाए सॉल्व करना. So this boundary condition applies when two materials are in contact. At the interface, both temperature and heat flux must be continuous to prevent sudden jump in energy. Now, imagine a composite wall of two different materials. Since heat cannot just disappear at the interface, the heat flux entering from one side must be equal to the heat flux leaving the other side. Now mathematically इसको कैसे एक्सप्रेस करेंगे तो टेम्परेचर विल बी इक्वल जो इधर जो इंटरफेस का टेम्परेचर है T1 ऑफ द फर्स्ट मटेरियल एंड T2 ऑफ द सेकंड मटेरियल दोनों सेम होगा एंड जो फ्लक्स है एंटरिंग मतलब कि जो फ्लक्स जो लीव कर रहा है पहले मटेरियल से जो फर्स्ट मटेरियल से फ्लक्स निकल रहा है विल बी इक्वल टू द फ्लक्स एंटरिंग द सेकंड मटेरियल एट द इंटरफेस इसका मतलब क्या होगा जैसे कि -K1 इसको मैथमेटिकली हम लोग डिस्क्राइब करेंगे -K1 dt1 by dx is equals to -K2 dt2 by dx where K1 K2 will be thermal conductivity of the two materials. Now this condition is crucial in layered systems like heat exchangers and composite insulation materials.
So हमने basically तो पहला the first two boundary conditions we have learned the temperature defined at the boundary and heat flux defined at the boundary. The third one is basically for two materials when they are in contact. जैसे कि assume first material to be iron and second material to be aluminum. So basically इसमें होता क्या है कि this is basically the interface condition. So अब इसमें the temperature at the interface of both the materials जो interface का temperature है of in our example iron and aluminum interface का temperature तो same ही रहेगा that is T1 that is temperature of iron at the interface and temperature of aluminum at the interface will be same the T1 equal to T2 and also the flux which will be leaving from iron and which will be entering to aluminum वो भी सेम रहेगा मतलब कि बेसिकली इसको मैथमेटिकली कैसे एक्सप्लेन करेंगे -K1 dt1 by dx is equals to -K2 dt2 by dx. So इसको अब briefly explain करूं तो this boundary condition applies when two materials basically are in contact. At the interface, both temperature and heat flux must be continuous to prevent sudden jump of energy. Now imagine a composite wall made up of two different materials, like we have taken iron and aluminum. Since heat cannot just disappear at the interface, the heat flux entering from one side must be equal to the heat flux leaving the other side. Now, this condition is crucial in layered systems like heat exchangers and composite insulation materials.
Okay, so far we have seen the three main boundary conditions. Now we will be jumping to the final boundary condition, that is convective boundary condition. This condition is applied when a solid is exposed to the fluid. That is, what happens in it, heat transfer is taking place by conduction as well as by convection. Inside the solid, the heat transfer is by conduction, and at surface, the heat transfer is by convection. For example, you have a cup of coffee. The conduction of heat inside the cup will be by conduction, whereas the heat transfer outside the cup will be by convection. Mathematically, this condition can be expressed using Newton's law of cooling. That is, Q equals to H in a multiply by T naught minus Tv. Here, H is your convective heat transfer coefficient, T naught is the surface at interface, and Tb is the bulk temperature or the outside temperature. So, this condition is mainly used in heat sinks, reactor fins, and cooling of electronic devices.
So basically, if we brief the boundary conditions, basically we have four. So पहला है कि बाउंड्री पे सरफेस बाउंड्री पे हम लोग को टेम्परेचर विल बी डिफाइंड. नेक्स्ट इज सिमिलर टू दैट बाकी बाउंड्री पे फ्लक्स विल बी डिफाइंड. नाउ द थर्ड वन इज अ बिट डिफरेंट कि उसमें व्हेन टू मटेरियल्स आर इन कांटेक्ट हम उसको यूज करते हैं मतलब इंटरफेस पे हम बाउंड्री कंडीशन लगाते हैं कंटिन्यूटी ऑफ टेम्परेचर एंड कंटिन्यूटी ऑफ हीट फ्लक्स दो बाउंड्री कंडीशन लगाते हैं. ये बेसिकली सिमिलर टू द प्रीवियस केस जो मोमेंटम शेल बैलेंस में किए थे, दैट इज ऑफ टू इमिसिबल फ्लूइड्स. देन देन द लास्ट वन जो हमने डिस्कस किया था इज कन्वेक्टिव बाउंड्री कंडीशन, जिसमें at a solid liquid interface, the normal heat flux component may be related the difference between the solid surface temperature that is T naught and the bulk temperature that is TB. मतलब उसमें बेसिकली हम न्यूटन्स लॉ ऑफ कूलिंग यूज करते हैं. बट इसमें आई लाइक टू ऐड वन मोर थिंग that is logical boundary conditions which will be useful in some of the cases. Like the logical boundary condition is basically that at any point q will be defined. मतलब q कभी भी undefined नहीं होगा, q will never be infinity. तो कभी भी हम लोग को r ऐसा मतलब कोई भी r पे हमको q होना ही चाहिए. तो दिस विल लीड टू फर्दर सिंप्लीफिकेशन जो हम लोग आगे देखेंगे लॉजिकल बाउंड्री कंडीशंस के यूजेस.